This video is a continuation of the last. We are discussing chapter 7 of Rao Bhim Chap about inner products. In particular, we are talking about what we need to really know about inner products before we enter into the murky details of the chapter. We start with a vector space V over R of dimension n. Then we take any basis B, B1 up to Bn. Then given any two vectors u and v in V, we can write them as tuples with respect to this basis. For example, u is u1 times b1 plus u2 times b2 all the way up to un times bn. Similarly, V has also an n-tuple representation with respect to that basis. Then we define the usual dot product in Rn as summation ui vi and use this to define a dot product in the vector space V. So we use this as the definition. Thus, in the definition of u dot v, we not only need the obvious inputs u and v, but also a secret input, an arbitrary basis b. If we change the basis, then u dot v also changes. Let us see an example of this in R2. When we say that the dot product between 1, 4 and 3, 2 is 1 times 3 plus 4 times 2 equal to 11, we are actually using the canonical basis 1, 0 and 0, 1. If, however, we use a different basis, say 1, 0 and 1, 1, then 1, 4 becomes minus 3 times the first basis vector plus 4 times the second basis vector. Similarly for 3, 2. So the tuple representation of 1, 4 with respect to this basis is minus 3, 4, and the tuple representation here is 1, 2. So with respect to this basis, the dot product between the same two vectors is now minus 3 times 1 plus 4 times 2, which is 5, different from the dot product between these vectors with respect to the canonical basis. In fact, in the world governed by this basis, this angle is the new 90 degree, because 1, 0 dot 1, 1 is equal to 0 in this basis. Also, the measurement of length is different. If you measure the length along this direction, then the unit is this length, which is 1. Nothing surprising here. But when you measure length along this direction, this length, which is root 2, is the new unit. The units of length along the other directions also change accordingly. Thus we see that the notation u dot v is really a function f u v b, that is, the dot product computed with respect to the basis script b. Now this function we can write in a more convenient notation as f subscript script b, same thing, but since we are not explicitly mentioning the basis, it is like a background information, so I put it in the subscript. Chapter 7 of Rao Bhim Chap wants to study the general properties of dot products, that is, the properties common to all such functions f subscript b. Since we are allowing an arbitrary basis b, we shall not use the term dot product anymore. Instead, we shall use the term inner product. We shall also denote the function f subscript b uv as parenthesis u comma v. Now notice that this is a somewhat confusing nameless notation for the function because the name is now omitted. In fact, parentheses are used for so many different purposes in math that some authors instead suggest that you use angle bracket here to reduce the confusion. However, we shall continue to use this notation. The discussion in Rao Bhim about inner products starts by listing three properties that characterize all such functions. We always start with V, a finite dimensional vector space over R, and we are defining a general inner product with this notation from V cross V to R. That is, you take one vector here, you take another vector here, combine them and you get a real number. The three properties are, number one, for all uv in V, this thing must commute. uv is same as vu. The second thing is one form of distributivity. For all ab in R, uvw in V, you have au plus bv, a linear combination in the first argument, splits out and the scalars come out. The third property says that for all vectors V, inner product of V with itself must be greater than or equal to 0, and it will be equal to 0 if and only if the vector is the 0 vector. It should be easy to see that for any basis B, the corresponding dot product function f subscript b satisfies all these three conditions. What is a lot less trivial is that if a function satisfies all these three conditions, then there will exist a basis b such that fb will be same as the particular inner product that we have given. Indeed, it is so very non-trivial that we do not have enough machinery at this stage to prove it. 3 points are worth noting here. First, we need this greater than or equal to 0 so that we can take square root to define length as length of V or norm V is square root of inner product of V with itself. Secondly, these definitions does not make any explicit use of the underlying basis, and they do not require the vectors to be expressed as a tuple, something like this u as u1 to un and v1 to vn. As a result, we can safely drop this finite dimension assumption. Now, this is a big step forward, as unlike the original dot product definition, this definition can be used for even infinite dimensional vector spaces. The third point is yet another possible generalization which is perhaps less easy to see. We can actually work with complex number C instead of R. Now, inner products indirectly define length via this relation. One of the most important things that we do with lengths is to compare them and make statements like one vector is shorter than another vector. Such a comparison is also inherent in a statement like the shortest distance of a point from a plane is the perpendicular distance. When we say shortest, we are basically comparing between lengths. Unfortunately, there is no comparison like greater than or less than in C. So, though we allow U inner product V to be some element in C, we must not allow V inner product V to be any arbitrary element of C. We still need this to be a non-negative real number. This we cannot relax. In order to guarantee this, we need to do certain technical modifications to the other properties, and all these technical modifications are based on the fact that if Z is any complex number, then Z times its complex conjugate gives you the modular square, which must be a non-negative real number. Now here are the modifications. We just need to put a bar over here. That's the only thing that will make us work with C. So for any u v in V, if you form the inner product u and V, you get a complex number. If you swap the order, in that case you get another complex number. One must be complex conjugate of another. We leave this exactly as it is, and we leave this exactly as it is. And this is the starting point of the murky details of Rao Bhim Chapter 7, which we shall take up in the next video.